Hey, what's up, PCH? This is a quick video on parent functions. How we're going to do this is go through each parent function we need to know, go ahead and plot a few points so that we can see how this graph comes to be. And then once you have the key points, that will really help you out for when we're doing transformations of functions for this lesson and on Monday as well. We'll go ahead and start with a line. I know this is super basic, but since it's here, might as well. Obviously, any value we plug in for x, that's exactly what our y is going to be. So if x is -2, y is -2, -1, -1, so on and so forth. And so when we graph that, I mean, you could graph every single one of these key points forever and ever and ever. Connect them all, you have the graph of a line. So the cool thing about a line is, as far as like being transformed, for the most part, I'd kind of think about any transformation in terms of like a vertical shift. A horizontal shift might look the same, but if you're thinking about like where's your y-intercept, I think that would be an easy way to think about a vertical shift. But for the most part, you're not going to really have transformations on your linear function unless it's a vertical shift, or maybe you have a slope that acts like your a value. And of course, we know how like slope works, rise over run. We've talked about lines. So I want to move on to some of the other ones. Let's talk about our absolute value graph. Again, same thing here. We can plug in just about any value for x. I'm just going to go ahead and start with -2, -1, 0, 1, and 2. When I plug in -2, the absolute value of -2 is +2. The absolute value of -1 is +1. Absolute value of 0 is 0. 1 is 1, 2, etc., etc. And so when we graph these things here, we see that we have a key point at 0, 0 at our origin, as well as 1, 1, 2, 2. You can kind of get the pattern, like you could keep going like this forever. As well as, oh, -1, +1, -2, +2, -3, +3. You kind of see that pattern. As far as when we are graphing transformations of absolute value functions, I would say your key points should be 0, 0, so your origin or your vertex for this absolute value function. And they should also be at least 1 point on each of these vectors or parts, pieces of our absolute value function. So 1 on this line and 1 on this as well. And so that could be like 1, 1. I think that makes sense. Especially in the like notes video, I talk about graphing amplitude. And so our 1 unit to the right rule, I think it makes sense to focus on both of the points that are just 1 unit to the right. In both directions of our origin. And so these would be our key points. And we'll see examples, of course, of graphing these in our examples video. But again, I just want to show you like how these graphs come to be and some of the key points that we'll be talking about. Let's talk about parabolas now. I'm going to go ahead, again, -2, -1, 0, 1, and 2. Make this smaller so it looks a little bit nicer. When I plug in a -2, I'll get -2 squared, which is a +4. -1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. When I graph that, I have a key point at 0, 0. Key point at 1, 1. Key point at 2, 4. Same with -1, 1. -2, 4. Connect those dots. Boom. We have our parabola. This is super huge. More so than the first two functions we've already talked about. When it comes to a parabola, it is super key that you understand that you have key points at 0, 0. You should be familiar with like 1, 1, -1, 1. Oops, that disappeared. As well as, I would even say 2, 4 and -2, 4. Why does this matter? Again, I think the most complicated transformation to actually graph on your own, without just plugging in points to the transformed function, is the amplitude. Reminder, again, I do talk about this at the end of the notes video, And you'll see like why these key points matter, why it is helpful for us to understand and know that, like, okay, if I'm talking about a parabola, I know the point 24 is on that parabola. Same with negative 24. Why is it important? Honestly, if you want to think about even what the next point would be, if we're at an x value of 3, well, 3 squared is 9. And so I would have a point here. Negative 3, 9 would also be a point on my graph. Things to keep in mind. Now for y equals the square root of x, our square root function. Now for the first three parent functions we've just talked about, every single time I've said, you know what, I'm just going to pick x values of negative 2, negative 1, 0, positive 1, and positive 2. However, let's think about this. I am telling you right now that I do not want to use negative 2 and negative 1 as x values for this function. Can you tell me why? Yes, hopefully you remember and recognize that you cannot take the square root of a negative number. That would give us an imaginary number, which those do not show up on our graph. Those are not defined values of our function. And so we do not want to plug in negative values for x. So I'm going to go ahead and start with 0. We can do 1, 2, or no. Whoops. I actually don't want to do 2. We'll talk about this in a second. Do 4, 9 maybe, etc., etc. Why am I picking all these random x values, you might ask? Well, I could plug in a 2 for x, but do I know what the square root of 2 is? Sorry, I certainly do not, because I know it's going to be some decimal number that it's going to be a pain in the butt to try and graph on my graph. And so I'm going to make life easier for me, and I'm going to make my key points that are going to end up at nice whole number coordinate points. And so the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And of course the square root of 9 is 3. So since I recognize that we are taking the square root of each of these numbers, I chose values of x that were perfect squares. And so when I look to graph these, I have 0, 0, I have 1, 1, I have 4, 2, and I have 9, 3. And that is where we get this square root function. We have nothing going on down here. We have nothing going on over here. All right. Again, super, super important that we know the key points for this function at our origin, at 1, 1, at 4, 2, at 9, 3. Because again, these are going to be the key points that we are graphing when we're doing transformations. All right, just 3 more left. X cubed. No, that's fine. X cubed, I know I'm going to be fine plugging in negative 2, negative 1, 0, 1, 2, so I'm going to stick with those again. Negative 2 squared. I'm curious, can you tell me what that's going to be? Hopefully you recognize that negative 2 cubed, I think I might have said squared, negative 2 cubed is negative 8. Some of us might have said it was positive 8, but remember, a negative number to an odd exponent will always be negative. Negative 1 cubed, negative 1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. Let's graph that. Negative 2, negative 8 down here. Negative 1, negative 1. Whoops, 0, 0, 1, 1, and then 2, 8. Boom, we have our cubic function. Again, whenever we are graphing functions, transformations, at minimum, we need 3 key points graphed. However, I would say whenever we're graphing a parabola, so y equals x squared, or a cubic function, which is what we just did, that you actually include 5 key points. Because if you just do these 3 here in the center, that doesn't tell you enough about what's happening up here, and I really want to make sure that you know for a fact what is happening beyond just this small space near the center of our graph. And so for, again, quadratics and cubics, I would say, hey, you know what? Let's do 5 key points. Let's do 5 key points. And those key points, I'm not going to write them on the graph. They're listed here in the table. You're going to want to know those points for this graph as well. Let's talk about a cubed root. Okay, this is where we get a little tricky, just like the square root. Can I plug in negative numbers for y equals the cubed root of x? Right up here, we could not, and I discussed why. Does that same thinking apply for y equals the cubed root of x? Absolutely not, right? Because we're taking an odd root, the cubed root in this case, you can have a negative value that results from that. And let me just write some values in here first, and then I'll explain like why that makes sense. Whoops, I don't want -2. So that's not a cube. It's not a perfect cube for us. -1, 0, 1, 8. When I plug in -8, the cubed root of -8 is -2. -1 is -1. 0. Cubed root of 1 is going to be 1. Cubed root of 8 is 2. Let's graph these things. -8, -2, -1, -1. Whoops, that's not right. -1, -1, there we go. 0, 0, 1, 1, and then 8, 2. How do I know this is true? Because literally we just did it over here. We said that we can have -2 cubed equals -8. Undoing that, the cubed root of -8 is -2. And so, yes, it is totally fine that we are plugging in negative x values into our cubed root function, and it's going to look a little something like this. This is going to be another function that I'd say, yeah, let's do 5 key points if possible. 5 key points if possible. Okay, last function is our rational function. I explained this a little bit in class, but I'll explain it very quickly again. A rational function is a function that has our variable in the denominator. So essentially it's a function that is a fraction. The issue here is that we cannot have our denominator equal to 0 because we can't divide by 0. That's undefined. And so for this function, what's going to make our denominator 0? Well, an x value of 0. And so we know x cannot equal 0. That's where we have a vertical dashed line, which is our vertical asymptote, at x equals 0. We will talk about this more when we talk more in depth about rational functions in Unit 2. But we also have a horizontal asymptote, a horizontal dashed line at along our x-axis at y equals 0. We cannot have our function defined along these points for this graph. One thing we notice is, hey, like let's plug in a -1 and a +1 into this function. So if we do a -1, 1 divided by -1 is -1. And so that's an x value of -1. We got -1. If we plug in a +1, 1 divided by 1 is +1. So 1, 1, boom, boom. That is all you need to graph for a rational function. Because you have the vertical asymptote and because you have the horizontal asymptote, those essentially act as key points in addition to like -1, -1, and 1, 1. Sorry, my graph is super bad. And so that's all you need to graph are those 2 key points in your asymptotes. If you want to plug in other numbers to see like why the graph looks this way, you absolutely can. Again, I did link this at the beginning, this like Desmos graphing calculator thing where you can kind of play around with the parent function, see what's going on, and I will highlight that rational function. Here at the end for us, we see this behavior as well as points 1, 1 and -1, -1. Folks, that is good on parent functions. We'll see you later.